Dear students, today we have a very informative session for the Indian Olympiad qualified in mathematics, which is conducted by the Mathematics Teachers Association of India and the Homi Bhabha Center for Science Education along with the Tata Institute of Fundamental Research is the conducting body, and the NBHM, National Board for Higher Mathematics, Department of Atomic Energy, Government of India is the responsible for the program related to Olympiad conducted in India for the purpose of the participation of students in International Mathematical Olympiad. So, today we will try to cover the eligibility for the Ioqm 2025-26 along with the syllabus which is required for the preparation of this Olympiad. The third is the full discussion upon the last year problems asked in the first stage, which is Ioqm, Indian Olympiad Qualified in Mathematics. As we know, there are total 5 stages for the International Mathematical Olympiad. The first is the Ioqm, Indian Olympiad Qualified in Mathematics. The second is RMO, which is Regional Mathematical Olympiad. The third stage is INMO, which is Indian National Mathematical Olympiad. The fourth stage is INMOTC, which is Indian National Mathematical Olympiad Training Camp, and the students qualified in the IMOTC, International Mathematical Olympiad Training Camp. Thereafter, the selected students, as the delegation of total 6 students, are the eligible for the participation to write the International Mathematical Olympiad. Every year there is a hosting country for this examination. So, there are many benefits of this Olympiad, but today we will just try to focus upon the point to point discussion related to this competition. The first is eligibility criteria for Indian Olympiad Qualified in Mathematics, which is first stage in accordance of the International Mathematical Olympiad. Here you can see the students born between August 1st, 2006 and July 31, 2013 and studying in class 8, 9, 10th, 11th and 12th are eligible to write the Ioqm 2025, and this is important to note that no students born on after August 1st, 2013 will be allowed to write Ioqm 2025. The students must be eligible to hold Indian passport. Provisionally students with OCI cards are eligible to write the Ioqm 2025 subject to condition and explained below. You can study here. Thereafter, these are the conditions, point number 2 and 3 you can study. The fourth is the students must not have qualified or scheduled to appear class 12 board examination earlier than 30 October 2025, and this is important to note that for future of class 12th board examination results, in order to meet eligibility criteria of Ioqm 2025 is not allowed, and any student adopting such a means will be disqualified from the Ioqm 2025. So, this is very important note, and every student should try to understand the point number 4. The fifth is the student must not have commenced or planning to commence studies in a university or equivalent institution by 1st June 2026. The point number 6 is the INMO 2025 awardees are eligible to write INMO 2026 directly without qualifying through Ioqm 2025 and RMO 2025, provided they fulfill the age criteria mentioned in the point number 1. They have not commenced or planning to commence by June 1st, 2025 studies in a university or equivalent institution and they fulfill the eligibility criteria for IMO 2026 and EGMO 2027. EGMO is basically European Girls Mathematical Olympiad, and this is also important to note that the OCI students are not eligible to represent India in INMO 2026 and EGMO 2027. So this is also important point. You can see the detail under the point 6. The point number 7 is it will be responsibility of a student to ensure that the above eligibility criteria are satisfied. In case it may found at any later stage of program that a student does not meet the eligibility criteria, he or she may be disqualified from the program. So I request that every student should fill the proper and true information regarding the registration of the Ioqm and further stages. Now, if we talk about the syllabus, here is the detail concerning the International Olympiad. This is the final stage, and the 6-member team, as I told you that the 6-member team selected at the end of IMOTC, which is International Mathematical Olympiad Training Camp, accompanied by a leader, a deputy leader and observers, represent the country at IMO held in July each year in a different member country of the IMO. The IMO contest consists of 2 written tests held on 2 consecutive days. On each days of the contest, the test consists of 3 problems and lasts for 4.5 hours. So this is very important point. You should understand that what is the format of this final stage examination. On each day of the contest, actually the IMO contest consists of 2 written tests held on 2 consecutive days. On each day of the contest, the test consists of 3 problems and lasts for 4.5 hours. India has been participating in the IMO since 1989. Students of the Indian team who receive gold, silver and bronze medals at the IMO receive a cash prize of rupees 5,000, 4,000 and 3,000 respectively. This is the current scenario for the winners of gold medal, silver medal and bronze medal. Along with, there are many benefits and advantages of this examination, and after, if you are clearing the stages, so there are many benefits for the stage wise qualification also. Students aiming to go through the Mathematical Olympiad program leading to international participation should note that Ioqm is the first essential step for the program. So you have to focus upon first stage because if you qualify the stage 1, then you will be eligible to participate for the second stage, which is RMO, Regional Mathematical Olympiad. Also for the students, a team of at most 4 girls students selected at the end of EGMOTC, accompanied by a leader, a deputy leader and an observer, represent the country at the EGMO held in April each year in a different European country. Actually, this information is useful for the girls students, and they can understand the point. The one more thing, which is after EGMO, APMO, which is Asian Pacific Mathematical Olympiad. This is also very important Olympiad examination. Here is the syllabus for the Mathematical Olympiad. Any aspirant for the International Mathematical Olympiad such as IMO, EGMO, APMO and the domestic selections round like RMO, INMO and also Ioqm. So they must be familiar with all the topics covered in NCERT mathematics books of class 8 to 12th also, and Must note that in addition to topics covered in point 1, above the following topics are to be given importance while preparing for the Olympiad examination. Must know that the major areas from the problems are posed by algebra, combinatorics, geometry and number theory, and that the difficulty level increases from RMO to INMO to IMO. So, this is the first topic, algebra. You can see these are the topics here in algebra. These are the recommended books for algebra. You can take reference from here. The second is plane geometry. You can take reference from the topics here. The recommended books are also mentioned. The third is combinatorics, basic enumeration, pigeonhole principle and its application. So, there are many other topics are, but you can take advantages from the recommended books which is internationally recognized. The fourth is number theory. This is very important topic, and as in my opinion you should try to start the preparation from the number theory, because there are many application of these topics are in algebra, in geometry and also in combinatorics. So, this is very important topic, and there are some reference books here. You can take benefit from here. These are the recommended books like Problem Primer for Olympiads, The Challenge and Thrill of Pre-College Mathematics, and Excursion in Mathematics. Fourth, Problem Solving Strategies. Fifth, Mathematical Circles. So, these are some important books. Many other interesting references may also be found in this book and Excursion in Mathematics mentioned above. It must be noted that the topic listed above do not constitute an exhaustive list. Problems asked in the RMO and INMO may include topics not explicitly stated above. One more important note here, that this is the only Olympiad which leads to participate in International Mathematical Olympiad. There are no any other Olympiads are recognized for this purpose. This is only the official recognized Olympiad by Government of India, and you should prepare for this Olympiad from the early class 8 to for the better result. Now, here we are starting the discussion. This is problem, total 30 problems are here. This is in Hindi. So, the students having language Hindi, they can go through the problems here. The problems are very interesting and frankly speaking not easy to solve without the clear concept from the basics. So, there are total 30 problems, and also the answer will be in integer type. So, there will be total 0 to 99 integers you have as the answer. So, there will be like grid based OMR sheet, and you have to color from 0 up to 99, which is the correct option. So, now here are some important points, as GCD AB denotes the greatest common divisor of integer a and b. the greatest common integer denotes the largest integer less than or equal to x. Somewhere this is like a closed bracket also, but the meaning are same. For a positive real number m, a square root of m denotes the positive square root of m. For example, a square root of 4 is equal to plus 2, unless otherwise stated, all numbers are written in decimal notation. So here the 4 important topics as we have seen in the syllabus discussion: the number theory, algebra, combinatorics and geometry. Like the problem number first, the smallest positive integer that does not divide, this is from number theory. The second question is also from number theory. The third question is also from number theory. The fourth question is from geometry. The fifth question is from algebra. The sixth question is problem is also from algebra. The seventh is from this is mixed problem from algebra and geometry. The problem number 8 is from number theory. The problem number 9 is from number theory and algebra. This is mixed problem. The problem number 10 is from algebra. The problem number 11 is from algebra. The problem number 12 is from geometry. The problem number 13 is from algebra. 14 is from number theory, combinatorics and geometry also. Actually there is a coordinate system, so this is also related to coordinate geometry. The 15th number problem is from number theory and algebra. The 16 is from functional equation from algebra. The 17 is from geometry. The 18 is from number theory. 19 is from combinatorics. 20 is from combinatorics. 21 is from number theory and combinatorics. 22 is from geometry and algebra and also from number theory. This is mixed problem. Problem number 23 is from number theory. The problem number 24 is from consider the set F of all polynomials whose coefficients are in the set of A. This is from algebra. The problem number 25 is from combinatorics. The problem number 26 is from algebra. 27th number problem is from geometry and also from number theory. So this is the mixed problem from geometry and number theory. The problem number 28 is from number theory and algebra. The problem number 29 is from number theory. The problem number 29th is from number theory, yes. The problem number 30 is from geometry, plane geometry and from some applications of number theory. So these are the total 30 problems we have to discuss. So here we are starting the question number first. This is the smallest positive integer that does not divide the factorial 9. which is in the form 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9. So to solve this, first of all, let n be a smallest integer, and this integer which we are assuming that does not divide 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9. We are just assuming that n be a smallest integer which does not divide this value factorial 9. So now we will do the prime factorization of 2 to the power 7 into 3 to the power 4 into 5 into 7. This is the prime factorization of given number. And now clearly we can see that here 2 and 7 factor of 2 will divide 9. So we can write this as we can see that 2 and 7 factor of 2 will divide 9 factorial. So in this case we have one more thing as in the form of 3 and 4 from this 2 to the power 7, and we can say that 3 and 4 factors of 3 and 4 factors of 3 will divide 9 in factorial. So the number like 2, 3, 2 to the power 2 means 4, 5 into 2 into 3, then 7, then 2 to the power 3 means 8, then 27, 3 to the power 3, and at last 5 into 2 will divide 9 factorial. So here we can choose the least positive integer that does not divide 9 factorial is 11. So we can write that the least positive integer after 10, because here 5 into 2 will give 10, so after 10 11 is the least positive integer. So we can say that 11 is least positive integer which will not divide 9 factorial. So 11 is the least positive integer, as the problem is given that the smallest positive integer that does not divide factorial 9. So here 11 is the least positive integer that will not divide 9 factorial. So now in the second problem, here we have the number of 4-digit odd numbers having digits 1, 2, 3, 4, each occurring exactly once each. So now what we can do, we can simply see that here, as the four digits ABCD is the forming number and is odd, and also for this D can take values as 1 or 3, and this will imply 2, and this is the possibility. And also A can take 3 values, and B also take the value 2, and for C will take 1. So the total values we have are 2 into 3 into 2 into 1. So here the total possible values are 12. So we can write the value 12, and this is the possible value, and this is the total number of 4-digit odd numbers having digits 1, 2, 3, 4, each occurring exactly once is 12. So we can write 12 as the answer. Here the problem number 3 is the number obtained by taking the last 2 digits of 5 to the power 2024 in the same order is. So the last 2 digits of 5 to the power 2024, and this will imply as 5 to the power 2024 is congruent to A mod 100. We can write this in the form. Again, 5 to the power 4 is congruent to 25 modulo 100. Same 5 to the power 2024 is congruent to 25 modulo 100, and because of this the last 2 digits in same order is 25. So here 25 is the solution. This is simply we have applied the concept of congruent and modulo. A is congruent to B mod n, means n divides A minus B, or we can say that n divides A for the remainder B. Exactly both the things are same. So here we have applied this concept to prove the divisibility, and here the last remainder is 25 when 5 to the power 2024 is divided by 100, and here this is the last 2 digits in the same order. In the problem number 4, let ABCD be a quadrilateral with angle ADC is 70 degrees, angle ACD is equal to 70 degrees, angle ACB is equal to 10 degrees, and angle BAD is equal to 110 degrees. Then the angle CAB we have to identify. So here ABCD is a quadrilateral, so we can simply make a diagram as ABCD is a quadrilateral here angle ADC is equal to 70 degrees. Here angle ADC is 70 degrees and angle ACD, angle ACD is also 70 degrees. Actually these two sides must be closer, because this seems to be the angle is exactly 90 degrees, but you can simply make the diagram as extending D to here. That's why this will be like the angle is acute less than 90 degrees, but you can just take the difference from here. The angle ACD is 70 degrees. Also angle ACB is 10 degrees. Angle BAD, yeah, this is quite satisfactory, because this is like the angle greater than 90 degrees, means obtuse 110 degrees, and we have to identify the angle CAB. Angle CAB, this is to be angle CAB. This angle we have to decide. So in triangle ADC we have the sum of two angles 70 degrees plus 70 degrees, this angle plus this angle, plus angle DAC, this angle, is equal to sum of the angles of a triangle is equal to 180 degrees. Now this will imply angle DAC is equal to 40 degrees. Now angle DAC plus angle CAB is equal to 110 degrees. So here angle CAB is equal to 110 degrees minus 40 degrees, and this is equal to 70 degrees. So finally the value of this angle is 70 degrees. So this is 70 degrees. In this problem, let A is equal to x by y plus y by z plus z by x, and B is equal to x by z plus y by x plus z by y, and the value of C is equal to x by y plus y by z into y by z plus z by x into z by x plus x by y, and we have to decide the value of modulus of AB minus C. So here we have just two equations are given, as here you can see this is the first equation and this is the second equation. So we can simply use these two equations as and also this is the third equation as in form of x, y, z and c. So we can write c as x by y plus y by z into y by z plus z by x into z by x plus x by y, and this is equal to a minus z by x into a minus x by y into a minus y by z. We are applying 1 and 2 equations to put the value. You can say like x by y plus y by z, x by y plus y by z is equal to a minus z by x. So we have just put the value here, and in the second case y by z plus z by x, so y by z plus z by x is equal to a minus x by y. So this is the value. And in the third case, z by x plus x by y, z by x plus x by y is equal to a minus y by z. So this is the third value here. And now this is equal to a into a into a. So this is aq minus the arrangement like z by x plus x by y plus y by z and into a square plus z by x plus x by z plus y by x into a and minus 1, and this is equal to a cube minus, you can see this is the value of a here. So this is a into a square, so this is a cube plus this is a and this is b, so this is a into b and minus 1. So finally this will cancel out, and the result will be like ab minus 1 and this is equal to c. So finally we can write 1 is equal to ab minus c. So here the value of ab minus c is 1. This is our solution. So this is 1 here. This is problem number 6. Find the number of triples of real numbers ABC such that a to the power 20 plus b to the power 20 plus c to the power 20 is equal to a to the power 24 plus b to the power 24 plus c to the power 24 is equal to 1. So now a to the power 20 plus b to the power 20 plus c to the power 20 is equal to a to the power 24 plus b to the power 24 plus c to the power 24 is equal to 1. And we have just the equations here as given in the problem, and this will satisfy in the condition as either a or b or c is equal to plus minus 1. This is the condition, and other have to be 0. So the second case, other on 0. So if we use a is equal to 1, then this will imply b is equal to c is equal to 0, and if we take a is equal to minus 1, then b is equal to c is equal to 0. So this is the two condition, and similarly for b and c, for b and c, if we use b is equal to plus minus 1, then this will imply a is equal to c is equal to 0, and if we take c is equal to same plus minus 1, then this will give a is equal to b is equal to 0. So total triples, we are just counting the total triples are the two from here, So the 2 we got from A1 and A minus 1, the 2 from B1 and B minus 1, and from C 1 and minus 1. So we have total, number of triples is 6. This is problem number 7. Determine the sum of all possible surface areas of a cube, two of whose vertices are 1, 2, 0 and 3, 3, 2. So we are just forming the diagram as this is 1, 2, 0, this is 3, 3, 2, and we are just forming this diagram as for the case 1. Now you can see the surface area is equal to 6 into square root of 4 plus 1 plus 4. This is whole square is equal to 3. So 3 square 9, 9 into 6 54. This is 54 square units. Now for the second case, this is 1, 2, 0 and this is 3, 3, 2, and we are just connecting this from this, the vertex here and vertex here. So now the length here, this is A, and same the length here A. So if we use this as case 2, this is second case. So now we have here 2a square plus 9 and a is equal to 3 by root 2, and here SA is equal to 6 into 9 by 2, and this is equal to 27 square units. Now here for the third case we have to draw the diagram as this is the point 1 to 0, and this is the coordinate 3, 3 and 2, and now we are just connecting the two vertices here and here. Now here square root of 3a is equal to 3, so a is equal to square root of 3, and the surface area is equal to 6a square is equal to 6 into 3, and this is equal to 18 square units, and the possible surface area is equal to 18 plus 27 plus 54, which we have already evaluated. This is the total possible surface areas as 18, here 27, and here 54. So now we are just adding all the three surface area, and this will be equal to 99. So here 99 is the total possible surface areas of this cube. In the problem number 8, let n be the smallest integer such that the sum of digits of n is divisible by 5 as well as the sum of digits of 0 plus 1 is divisible by 5. What are the first two digits of n in the same order? So let sum of digits, and we have to form the n digit number. So n digit number is equal to 5 lambda, and now the sum of digits of n plus 1 numbers is equal to 5k. We are just assuming. So now here 1, 2, 3, 9, 10, 11, 19, 20, 99, 100, and we are just forming the set as this is for 8 and 1, this is for 8, for 17, and this will continue as this will be for the total 26, and this will be for total 35. Again 50 for 50,000, and this will be for 35. So the smallest number will be here. We can write the smallest number is equal to 49999, and the first two digit is 49. This is here. So 49 is our answer. In the problem number 9, consider the grid of points x is equal to mn, and mn is in the interval of 0 and 4, including 0 and 4. We say a pair of points in ordered pair AB and CD in X is a night move pair if C is equal to A plus minus 2 and D is equal to B plus minus 1, or C is equal to A plus minus 1 and D is equal to B plus minus 2. The number of night move pairs in X is, we have to identify the number of night move pairs in the set X. So first of all, we have to form the grid here. Here we have drawn the 5 vertical lines, and here here 4 horizontal lines. And now we are connecting the points as we are starting from the bottom line. This is from here. Also this is from here. This is from here. this will not be included. Now we are naming every vertex will form the two connections. This is 1, 2, 3, 4, 5, 6, this is 7, 8, 9, 10, 11, this is 12, this is 11, this is 12, this is 13, this is 13, this is 14, this is 15, this is 16, this is 17, this is 18, this is 19, this is 20, this is 21, this is 22, this is 23, this is 24, this is 25, this is 26, this is 27, this is 28, this is 29, this is 30, this is 31, this is 32, this is 33, and this is 34. So here we have made the grid. You can see here by connecting all the vertices of the squares, and each line represents the allowed move from one and point of line to other end point of line. We can see the movement allowed is 3 by 2 and 2 by 2 rectangle, because this is just I am highlighting by the this is the square, and also the grid is connected in such boxes, which is the in rectangular form. So in each rectangle there are 4 moves allowed, and total number of rectangle are 12, we can see. So here we can write the total allowed move will be 24 into 2, 48, 12 into 4 is equal to 48. So 48 will be the total number of move. And one thing also is important to mention, that the movement allowed in 3 by 2 and 2 by 2 rectangle, vertical and horizontal. So in each rectangle there are 4 moves allowed, and total number of rectangle are 12. Total moves allowed is equal to 4, and we have total number of rectangle is equal to 12. So here total number of allowed move is equal to 12 into 4 is equal to 48. Here in this problem, determine the number of positive integral values of p for which there exists a triangle with sides a, b and c, which satisfy a square plus p square plus 9 into b square plus 9c square minus 6ab minus 6pdc is equal to 0. Now we can transform this equation as you can see a square plus here 9b square, so a square plus 9b square minus 6ab will be a minus 3b whole square, same pb minus 3c whole square is equal to 0. So here the sum of two squares is equal to 0 if and only if both the quantities are 0. So we can write a is equal to 3b and also pb is equal to 3c. So from here we can write c is equal to pb by 3. If a is the largest side, so in this case we have the sum of two sides must be greater than the third side, so b plus pb by 3 is greater than 3b, and from here 3 plus p is greater than 9, so p is greater than 6. So this is the first observation. Now if we are assuming instead of a, c is the largest side, so in this case we are mentioning here if c is the largest side, so in this case 3b plus b is greater than pb by 3, and from here p is less than 12, and from here if we take this the second case, so by concluding these two cases, this is the first and this is the second, so in this case we can identify the value of p as the possible values may be 7 greater than 6, so 7, 8, 9, 10 and 11. So total number of positive integral values of p is 5, 1, 2, 3, 4, 5. So total values are 5 values for p. In this problem, the positive real numbers ABC satisfy the values given this, and we have to find the value of 1 by a plus 1 by b plus 1 by c. Now this is like 3c by a plus 1 plus 3c by a plus 1 plus a by 2b plus 1 plus 2b by 3c plus 1, this is given 1, and 1 by a plus 1, 1 by 2b plus 1 and 1 by 3c plus 1 is equal to 2. So now we are writing this in the order as this can be written as 3c by a plus 1 plus a by 2b plus 1 plus 2b by 3c plus 1, and just we are writing in the order as in the second equation a plus 1, 2b plus 1 and 3c plus 1 are the denominators respectively. So we are just adding these two equations. So this will be like 1 by a plus 1 plus 1 by 2b plus 1 plus 1 by 3c plus 1 is equal to 1 plus 2 is equal to 3. So this will be like 3c plus 1 by a plus 1 plus a plus 1 by 2b plus 1 plus 2b plus 1 by 3c plus 1, and this is simply equal to the value in right hand side 3. Now here if we apply the arithmetic mean and geometric mean inequality, because we have the positive real numbers ABC, so in this case we can write, we are applying the AMGM in all the three terms. So this will be like 3c plus 1 by a plus 1 plus a plus 1 by 2b plus 1 plus 2b plus 1 by 3c plus 1. This is divided by 3 and this will be greater than or equal to 1 to the power 1 by 3. So now 3c plus 1 by a plus 1 is equal to 1 and 2b plus 1 by 3c plus 1 is equal to 1, and for this a plus 1 by 2b plus 1 is equal to 1, and this will imply a plus 1 is equal to 2b plus 1, and this will be equal to 3. So this will be equal to k, as we are just assuming. Now here 1 by k plus 1 by k plus 1 by k is equal to 2, and this will be like 3 by k is equal to 2, and this will imply k is equal to 3 by 2. Now a is equal to 1 by 2, b is equal to 1 by 4, and c is equal to 1 by 6, and this will imply 1 by a plus 1 by b plus 1 by c is equal to 2 plus 4 plus 6, and this is equal to 12. So we got the value 12 of 1 by a plus 1 by b plus 1 by c. Now this is important to understand that we have applied the AM-GM inequality. AM is greater than or equal to GM if we have the terms a plus b plus c by 3 is greater than or equal to ABC power 1 by 3. So this is how we have applied here in this problem. Here in this problem, consider a square ABCD of side length 16. Let EF be points on CD such that CE is equal to EF is equal to FD. Let the line BF and AE meet in M. The area of triangle MAB we have to decide. So now if actually to solve this problem we can use the construction method and also the coordinate geometry. So I will try to solve this problem by the application of coordinate geometry, for which you can see this is the axis x and y, and now this is point B, this is point A, this is point D, and this is point C. I am taking this point C at origin because of the simple solution and avoiding the more calculation. So just this is a technique to plot the point on origin. Now here E is the point and E is connecting to A, and here this is point F and B is connecting to F, and this is point M which is 8, 4. This is the point 0, 16. This will be the point 16 and 16, the point D will be 48 by 3, 0, and this is the point E, 16 by 3, 0, and the point F is 32 by 3, 0. Now, and origin is 0 and 0. So equation of line BF, we can decide equation of line BF we can write as 2y plus 3x minus 32 is equal to 0, and M we have here 8, 4. So area of triangle AMB, now we can decide. So to calculate the area of triangle AM and B, we can simply use the concept of the finding the method of area of triangle using determinant if the coordinates of the vertex are given. So this will be equal to 1 by 2, 0, 16, 1, 0, 16, and also for the second 16, 16, 1 and 8, 4, 1. We have used the vertex as 0, 16, 8, 0, 16, 8, the second 16, 16, 4, 16, 16, 4 and 1, 1, 1 will be the third column of this determinant. And we are using just this symbol because area cannot be negative, so we are taking the modulus. Now this will be equal to 1 by 2, solving the determinant. This is minus 16 into 8 plus 1 into 64 minus 8 into 16. So this is like 1 by 2 minus 16 into 16 plus 64, and this is equal to 16 by 2 into 4 minus 16, and this is 8 into 12, because this is basically minus 12, so because of modulus this will be like 96. So this is how the area of triangle we have evaluated. So area of triangle MAB is equal to 96 square units. Now in this problem, three positive integers ABC with A is greater than C satisfy the following equations. AC plus B plus C is equal to BC plus A plus 66 and A plus B plus C is equal to 32, and we have to evaluate the value of A. So now this is given that A is greater than C. A is greater than C. So here AC plus B plus C is equal to BC plus A plus 66, and A plus B plus C is equal to 32. Now this will imply C into A minus B plus B minus A plus C is equal to 66, and this will imply A minus B into C minus 1 plus C minus 1 is equal to 66 minus 1 implies c minus 1 we can take common, so this is a minus b plus 1, and this is equal to 65 is equal to 1 into 65 is equal to 65 into 1. We can write this in the way, and this is simply 5 into 13 or 13 into 5. So for the another case here, for the second case, this is in the first case. The second case will give the result as c minus 1 is equal to 65. So a minus b plus 1 is equal to 1, and this will imply c is equal to 65 plus 1 66, and also a plus b plus c is equal to 32, and this is basically not possible. So this is the first case. Now for the case 2, we can see here that c minus 1 is equal to 1, so a minus b plus 1 is equal to 65, and for c is equal to 2, a minus b is equal to 64, and here a plus b plus c is equal to 32, and this will imply a plus b is equal to 30. So now if we use a as 2a is equal to 64, so this will be like a is equal to 47 and b is equal to minus 17. Again, this is not possible. Now for the third case, if we are using the case 3, so this can have c minus 1 is equal to 5 and a minus b plus 1 and for case 3, c minus 1 is equal to 5 and a minus b plus 1 is equal to 13. So c is equal to 6, and the value of a minus b is equal to 13 minus 1 is equal to 12, and here is the possibility for a and b 19 and 7. For case 4, we have c minus 1 is equal to 13 and a minus b plus 1 is equal to 5. So here c is equal to 14 and a minus b plus 1 is equal to 5. So a minus b is equal to 4, and we have a is equal to b is equal to 18. So this will imply a is equal to 11, but from the case of the given problem, a is less than c, so only a is equal to 19 is the possibility. So we have the value of a is equal to 19. In the problem number 8, we have solved this as this method. In this problem, let n be the smallest integer such that the sum of digits of n is divisible by 5, as well as the sum of digits of n plus 1. n plus 1 is also divisible by 5. So what are the first two digits of n in the same order? So to solve this, we can also solve this problem as we have to find the starting two digits of the number which is least and divisible by 5. So let the sum of digits of natural number denote the sum of digit of natural number m, and we have to notice that Sm plus 1 is equal to Sm plus 1 if m denotes the case which is not ending with 9. We have to mention here not ending with 9, and we can see that if the number n does not end with 9, then Sn and Sn plus 1 would only differ by 1, so would only differ by 1. So both of them cannot be divisible by 5, and hence we can write n is equal to x9 bar. Now similarly, if x does not end with 9, x does not end with 9, so in this case Sn and Sx, we can write the relation as Sn is equal to Sx plus 9, and this will be like Sn plus 1 is equal to Sx plus 1, and this is equal to S of x plus 1 from this condition. So now this is a contradiction, because this will imply Sn plus 1 minus of Sn, and this will be equal to 8, which is contradiction. So we can simply have n is equal to y99 bar, and this will be again y must end with 9, so S of n plus 1 minus Sn equals 9 plus 9 minus 1, 17. This is also contradiction. So if we proceed in this way, that we would get n is equal to like the 4 times 9 and the smallest value of n such we take, then it would be like 9 plus 9 plus 9 plus 9, which is 36, and if we add 1 here, this will be 37. If we add 2 here, so this will be 38. If we add 3 here, this will be 39, and if we add 4, this will be 40, and this is divisible by 5. So the list value is 4 on the first place here instead of Z, and now we have the number like 49999, and the next number is 50,000, and both the numbers are divisible by 5. So mathematically we can write that the number, this is the least positive integer for which the next number, and this number itself is divisible by 5. Also we can write that 9 plus 9 plus 9 plus 9 is equal to 36 is 1 modulo 5. So we need here Z to be 4 modulo 5, and here we got the value of Z as 4, which is here. So this is the final solution. Now we are returning on question number 14. Here in the question number 14, initially there are 3 to the power 80 particles at the origin. At each step the particles are moved to points above the x-axis as follows. If there are n particles at any point xy, then the greatest integral value of n by 3 of them are moved to x, and the ordinate is y plus 1, and the remaining to x minus 1 y plus 1. For example, after the first step there are 3 to the power 79 particles, each at 1 1 0 1 and minus 1 plus 1. After the second step there are 3 to the power 78 particles, each of them at minus 2 2 and 2 2, and 2 into 3 to the power 78 particles, each of them minus 1 2 and 1 2, and 3 to the power 79 particles at 0 2. After 80 steps the number of particles at 79 80 is. So in this problem we have the coordinates of the situation of particles. So now first of all we have to construct the coordinate system as here. Now we are just taking the abscissa and ordinates of now here we have the coordinate system now, and at first here is the point which is a by 3. This is the first situation. Now after that, this is the point a by 3 square. This is the second situation. Now for the third situation, we have to choose the point here, and this is the point 3 to the power 3 in denominator, and this is the third situation. Now the point here and the point here, this is 3a by 3 square, and the point here, this is 2a by 3 square, and also the point here, the point here, this is 3a by 3 to the power 3, and here is the point, this is 4a by 3 to the power 4, and the point here, this is a by 3 to the power 4. Now we have also the point here, this is a by 3, and now we can add here the point, this is a by 3 to the power 3 plus 2a by 3 to the power 3, and this is the starting point, origin. So now we can simply write the nth step of particle at the coordinates n minus 1 n, and this is equal to na by 3 to the power n, as we are just taking the advantage of this pattern. So like this is 2a by 3 to the power 3, this is 3a by 3 to the power 3. So we have to take this point and this pattern as 3a 3 to the power 3, and now this is 4a 3 to the power 4. So this is na and 3 to the power n is the position of nth particle at the point n minus 1 and n. Now at the 80th step, the particle at the coordinates on 79 and 80, and this will be like 80a by 3 to the power 80 from this format. So if a is equal to here 380, hence total steps here, the number of particles at 79 and 80, we have the total number of particle will be 80 at the step 79 and 80. So this is the total number of particles at 79 and 80th coordinate system. Now in this problem, let x be the set consisting of 20 positive integers n, n plus 2, n plus 38, the smallest value of n for which any three numbers a, b, c belongs to x not necessarily distinct, and form the sides of an acute angle triangle is. So now the set is n, n plus 2 up to n plus 38, this is given. Now this is a, b and c belongs to x, and for any ABC, the first case is the triangle should be formed, and the second is the triangle should be acute. So only one angle can be obtuse at maximum. So the first case, a less than b and less than equal to c. So for triangle, this is the condition that a plus b, the sum of two sides, must be greater than third side. So all possible combinations here, even if a, b are smallest, a equal to b equal to n, and this will imply n plus n greater than n plus 38. So this will imply n is greater than 38 and the triangle will be formed. Now for the second case, this is the first condition, and for the second condition, that is, now we are using cosine formula for the largest side and the longest angle, because we know that largest side will give the longest angle and the longest angle will give the largest side. So in this case, cos C is equal to a square plus b square minus c square by 2ab, and this is greater than 0 for acute triangle. And this is like we have a square plus b square minus c square, because 2ab is not equal to 0. So here we can write a square plus b square minus c square is greater than 0, and for triangle, for all a, b, c belongs to x, and this is n square plus n square minus of n plus 38 whole square is greater than 0. So this is n square minus 76n minus 38 square, n square 2n square, 2n square minus n square is equal to n square, and minus 2ab, 2 into 38 into n, so 76n minus 38 square, and this is greater than 0, and this will imply n must be greater than 91.74. so the value 91.74, and the next after the value is 92. So here n must be equal to 92. This is the integral value of n. So here the smallest value of n for which any three numbers ABC not necessarily distinct from the sides of an acute angle triangle will be 92. In the problem number 16, let the function real to real be a function satisfying the relation 4 times function of 3 minus x plus 3 times function of x is equal to x square. For any real number x, find f of 27 minus f of 25 to the nearest integer. So now here we have 4 times the function of 3 minus x plus 3 times function of x is equal to x square, and this is for all x belongs to real number. 4 times function of 3 minus x plus 3 times function of 3 minus x is equal to 3 minus x whole square, and this is like 4 times function of x plus 3 times function of 3 minus x is equal to x minus 3, and now 12 times f of 3 minus x plus 9 times function of x is equal to 3x square, and here 12 times function of 3 minus x plus 16 times function of x is equal to 4 times x minus 3 whole square, and this will imply the 7 function of x is equal to 4 times x minus 3 whole square is equal to 3x square. Now here we can see that this is equal to the x square minus 6x plus 9. So here this is 4 times 24 square minus 3 into 27 square, and this is minus 4 times 22 square minus 3 into 25 square, and this is equal to 4 times 24 square minus 22 square plus 3 times 25 square minus 27 square, and this is equal to 4 times 46 into 2 plus 3 times 52 into minus 2, and this is equal to 8 into 46 into 6 into 52, and here the value of f of 27 minus f of 25 is equal to 1 by 7 into 46 into 8 minus 6 into 52, and this is equal to 56 by 7, which is equal to 8. So the final value of f of 27 minus f of 25 is equal to 8 we have. Here this is the problem number 17. Consider an isosceles triangle ABC with sides BC is equal to 30, CA is equal to AB is equal to 20. Let D be the foot of perpendicular from A to BC. M is the midpoint of AD. Let PQ be the chord of the circumcircle of triangle ABC such that M lies on PQ is parallel to BC. Then the value of PQ is we have to find out. So now first of all we have to draw a triangle like this. The triangle is isosceles. This is A, this is B, and this is the vertex C, and also this is given there is a circumcircle on this triangle ABC. So we know that the circumcircle is what? If the perpendicular from the vertex we are drawing here, and this is the circumcircle, and now there is a parallel line PQ parallel to BC, and here this is the point of intersection of the perpendiculars from the vertex A and B. Now we have the coordinates of the points. For B we have minus 15 and 0. We are taking this at origin, so 0 0. This is 15 and 0. This is 0 and 5 root 7. Now we have the equation of a straight line PQ, equation of PQ as y is equal to 5 root 7 by 2 and perpendicular bisector of AC y minus 5 root 7 by 2 is equal to minus 1 by 5 root 7 minus 0 by 0 minus 15 into x minus 15 by 2, and this will imply y minus 5 root 7 by 2 is equal to 15 by 5 root 7 into x minus 15 by 2. Here we are using the straight line if points are given. So like y minus y1 is equal to minus 1 by slope into x minus x1, and here this is y2 minus y1 upon x2 minus x1. Now we have the center, and which is the intersection of perpendicular bisectors, as we can write the coordinate of the center as 0 minus 5 by root 7. This is like minus 5 root 7 by 7, and we are simply rationalizing the denominator. So here this will be for the equation of circle. We can write the equation as we have like x minus 0, this is x1, this is y1, so x minus x1 whole square plus y minus y1 whole square is equal to radius squared. So this is x minus 0 whole square plus y plus 5 root 7 by 7 whole square. This is equal to 5 root 7 plus 5 root 7 by 7 whole square, and this is like x square plus y plus 5 by root 7 whole square is equal to 25 into 7 into 64 by 49 is equal to 25 into 64 by 7, and this is for the intersection with the parallel line PQ. We have y is equal to 5 root 7 by 2. We are just mentioning that intersection with PQ, which is parallel to BC. So now we have x square is equal to 25 into 64 by 7 minus of 5 root 7 by 2 plus 5 by root 7 whole square, and this is equal to 25 into 64 by 7 minus of 1 by 4 into 7 into 45 square. So now here we have x square is equal to 25 into 64 into 4 minus 45 square by 28 and this is equal to 5 square by 2 square into 64 into 4 minus 81 by 7, and this is equal to 5 square by 2 square into 25, and finally this will imply the value of x as plus minus 25 by 2. This is the distance, like 25 by 2 minus of minus 25 by 2, and this is the value. Simply 50 by 2 is equal to 25. So finally we have the distance is equal to 25. Here in the problem number 18, let PQ be two digits number, neither of which are divisible by 10. Let R be the four digit number by putting the digits with P followed by the digits of Q in order. As PQ vary, a computer prints R on the screen if GCD of P and Q equals 1 and P plus Q divides R. Suppose that largest number that is printed by the computer is n. Determine the number formed by the last two digits of n in the same order. So now, first of all, we have the division algorithm for R and Q, as R equals 100 R plus Q, and this is for R plus Q divides R is equal to 100 R plus Q. This will imply R plus Q divides 99 R, but here GCD of R plus Q and R equals 1. So this will imply R plus Q divides 99, and hence this is for R plus Q equals 33 or 99, and for n, which is the largest number that is printed by the computer is n. This is to be maximum. When R plus Q is equal to 99, where R is equal to 89 and Q is equal to 13. So we have the value of Q is 13 and R is equal to 89. So here the number formed by the last two digits of n will be 13. In this problem, consider 5 points in the plane with no three of them collinear. Every pair of points among them is joined by a line. In how many ways can we color these lines by red or blue so that no three of points formed a triangle with lines of the same color? So for this, we have, in the first case, we are taking a rectangle. Here B, C, D and E, and A is the point above this rectangle, and we are just joining all the vertices with each other. Now here this is for the first case. There will be exactly 5 red sides. The 2 ways. This is corresponding to each other, and also as color of other sides got fixed, so we have to take the second case. In the case 2, if we use the same like this is B, C, D, E, A, and here exactly 4 red sides, and this is not possible because there will be 0 ways as color of other sides got fixed, and there will be one triangle which will have all sides red on black, so this case is not possible. And we can write here that 0 ways as color of the other sides got fixed, and there will be one triangle which will have all sides red on black. Now for the third case, we have B, C, D, E, A. This is case 3. In this case, exactly 3 red sides, and this will be consecutive, and this is also not possible, so this will be 0 ways, and this is the same reason as case 2. Now for the case 4, we have exactly for case 4 we can see Here this is exactly two consecutive red sides, and this is the only one way of coloring as color of other sides got fixed, and hence two ways corresponding to each color for the given diagram you can see. Now the total number of ways will be like total number of ways we can calculate now is equal to the 2 from here, and 5c1 into 2, this will be equal to total 12 ways. Here 5c1 ways of simply choosing 2 will active rates. In the problem number 20, on natural number n, you are allowed to two operations. The first is multiply n by 2, and the second subtract 3 from n. For example, starting from 8, you can reach 13 as follows: 8 to 13. You need 2 steps, and you cannot do in less than 2 steps. Starting from 11, what is the least number of steps required to reach 1 to 1? So here we are starting from 11, so 11, and in some steps this will be 121, and this is minimum steps. Now we can notice that for each step the number is a natural number, so we have to reverse the process, and now we start from 121, and now condition will be like here n by 2, or this will be n plus 3. Now 121 cannot be divided by 2 as the result, and will not be natural number, and for minimum step it is better to keep dividing till we get on odd numbers. So 121 plus 3 is equal to 124. This is first. For the second step, 124 by 2 is equal to 62. For the third, 62 by 2 is equal to 31. For the fourth, 31 plus 3 is equal to 34. For 5, it will be like 34 by 2. For the sixth, 17 plus 3 is equal to 20. Now for the seventh, 20 by 2 is equal to 10. For the eighth, 10 by 2 is equal to 5. For the ninth, it will be 5 plus 3 is equal to 8. Now for the 10th step, this is 8 plus 3, and now we can see that it does not make sense to go half, as one move to reach 11, so the minimum 10 moves is required. We can mention here that it doesn't make sense to go half, as one move to reach 11, so there will be 10 moves in total. So what is the number of steps required to reach 121? So there will be total 10 minimum steps to reach at 121. In the given problem, an integer n is such that the greatest integer value of n by 9 is a 3 digits number with equal digits, and n minus 172 by 4 is 4 digit number with the digits 2024 in some order. What is the remainder if n is divided by 100? So now let n minus 172 by 4 is equal to k, where k belongs to integer, and n minus 172 by 4 belongs to k and k plus 1, and here we have to take k plus 1 in open interval. Now n minus 172 belongs to 4k, and 4k plus 4, this will be closed and this will be open, multiplied by 4, and now n by 9 belongs to 4k plus 172 by 9 and 4k plus 176 by 9. This is for n by 9 belongs to the set of elements 1 1 1 2 2 2 3 3 3 up to 9 9 9, and this will imply 4k plus 176 by 9 greater than a. This will be greater than 4k plus 172 by 9 for a belongs to 1 up to 9. For a is equal to 9, we have for the value of a is equal to 9, we have k belongs to 2203 0.75 2204.75, and this will imply k is equal to 2204. Now n minus 172 by 4 is equal to 2204, and this will form the first equation in terms of n. And now we have simply for the second case, n by 9 is equal to 999. This is the second case. So from 1 we have n minus 172 by 4 belongs to 2204, 2205, and this will imply n belongs to 8988, 8992, and from the second case we have n by 9 belongs to 999 and 1000, and this will imply n belongs to 8991, 9000, and this will imply n is equal to 8991. So here the required number will be 91 we have. So here we can write the required remainder when n is divided by 100 is 91. So this is the required solution we have. In the given problem, there is a triangle. We have this is a right angle triangle A, B and C, and this is right angle at A, so this is 90 degrees, and here D be the point on BC such that AB plus BD is equal to AC plus CD. Suppose BD is to DC is equal to 2:1, and if AC by AB is equal to m plus square root of P by n, where m and n are relatively prime positive integers and P is prime number. Now we are connecting the point D from A. This is x plus y, this is x, and we are assuming the distance here y, and this is 2x. Now we have simply given that AB plus PD is equal to AC plus CD. So y plus 2x is equal to AC plus x, and this will imply AC is equal to x plus y. Now by the Pythagoras theorem, x plus y whole square plus y square is equal to 3x whole square, and this will be by opening this bracket x square plus 2y square plus 2xy is equal to 9x square, and this will be equal to 8x square minus 2y square minus 2xy is equal to 0, and this will imply 4a square minus a minus 1 is equal to 0. So here we can write the value of a as simply a is equal to x by y. Now here a is equal to 1 plus minus a square root of we are just applying the discriminant rule for finding the value of a here. So a is equal to 1 plus minus a square root of 1 plus 16 by 8, and this will be equal to 1 plus minus a square root of 17 by 8, and this will imply the value of a is 1 plus minus root 17 by 8. So now here AC by AB is equal to 1 plus x by y is equal to a plus 1 is equal to a plus 1, and now we can write AC by AB is equal to 1 plus square root of 17 by 8 plus 1, and here AC by AB is equal to 9 plus square root of 17 by 8, and this will imply m plus n plus p is equal to 34. So now we have the value of m plus n plus p is equal to 34, and this is the required value. We have. So now here in this problem number 23, consider the 14 numbers 1 to the power 4, 2 to the power 4 up to 14 to the power 4, the smallest natural number n such that they leave distinct remainders when divided by n. So now we have 1 to the power 4, 2 to the power 4 up to 14 to the power 4. So here we can use the concept of A is congruent to B mod n, means n divides A for remainder P, or n divides A minus B. So simply here x to the power 4 is congruent to A mod n, and y to the power 4 is congruent to B mod n, and this is like in a way that A is not equal to B for x is not equal to y, and also xy belongs to 1, 2 up to 14. Now we have x to the power 4 minus y to the power 4 is congruent to A minus B mod n, and also we are factorizing this as x minus y into x plus y into x square plus y square is congruent to A minus B mod n, and this will imply n does not divides x minus y into x plus y into x square plus y square. So now we have to find minimum n with this condition. We have this condition. So according to this condition we have to find the minimum n. So for minimum n we have clearly n is greater than 27 as x plus y belongs to 3 up to 27, and now for n is equal to 28, the value greater than 27, 28 is the acceptable value. So for n is equal to 28, x is equal to 6 and y is equal to 8 will work. So now we have n is equal to 29, x is equal to 5 and y is equal to 2 also works, and n is equal to 30, x is equal to 8 and y is equal to 2 also works. So for n is equal to 31 there are no such x and y. So here we have the accepted values are here. Now we have to see that if we take the values as the divisor 31 divides x minus y into x plus y into x square plus y square, and this is important to understand, this must be prime factors. So now this is clear that 31 does not divides x square plus y square, and also 31 does not divides x minus y into x plus y. So here 31 will be the value, and we had a need of a smallest natural number n such that they leave distinct remainders. When divided by n will be 31 here. So here 31 is the value. Now in the problem number 24, consider the set f of all polynomials whose coefficients are in the set of 0, 1. Let qx is equal to x cube plus x plus 1, the number of polynomials px in f of degree 14 such that the product px into qx is also f is. So now we have px into qx is equal to polynomials in power 14. So this is like x cube plus x plus 1, and here px is equal to x to the power 14, and this will give the first case. Now px is equal to x to the power 14 plus x square, and this will imply alpha is equal to 10, 9, 8 up to 10. This is total number of the 10, 9, 8 7, 6, 5, 4, 3, 2, 1. So now we have px is equal to x to the power 14 plus x to the power alpha plus x to the power beta, and here this will give the value alpha. We have for 10, when we have alpha is equal to 10, beta is equal to 6, 5, 4, 3, 2, 1 and 0. When alpha is equal to 9, beta is equal to 5, 4, 3, 2, 1, 0. When alpha is equal to 8, beta is equal to 4, 3, 2, 1, 0. When alpha is equal to 7, beta is equal to 3, 2, 1, 0. When alpha is equal to 6, beta is equal to 2, 1, 0. When alpha is equal to 4, alpha is equal to 5, then beta is equal to 1, 0. When alpha is equal to 4, beta is equal to 0. So here px is equal to x to the power 14 plus x to the power alpha plus x to the power beta plus x to the power r, and here alpha is equal to 10, beta is equal to 6 and r is equal to 2, 1, 0. Alpha is equal to 10, beta is equal to 5 and r is equal to 1, 0, and alpha is equal to 10, beta is equal to 4, r is equal to 0, and total number of cases here we have the total number of cases here 25, and here total number of the cases is 6. And now for the case which is different for alpha is equal to 9, beta is equal to 5, r is equal to 1 0, and beta is equal to 4, r is equal to 0. So here total 3 cases. And now when alpha is equal to 8, beta is equal to 4, r is equal to 0, this is single case. And now the total number of cases when we add, so it will be 1 plus 11 plus 28 plus 6 plus 3 plus 1, and this will be total 50 cases we have. So total number of cases are 50, and these are all the possible cases. Now in the problem number 25, we have a finite set M of positive integers or distinct perfect squares and the number 92. The average of the number in M is 85. If we remove 92 from M, the average drops to 84. If n square is the largest possible square in M, what is the value of n? So now here this is given that the positive integers of distinct perfect squares. So now a1 square plus a2 square plus a3 square plus up to a0 square plus 92 and divided by n plus 1 is equal to 85. We are assuming this the first equation. Now if we remove 92, then this will be like a1 square plus a2 square plus a3 square plus dot 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 up to an square divided by n is equal to 84, and we are assuming this as equation number 2. So from 1 and 2 we have 84n plus 92 into 85n plus 85, and this will imply n is equal to 7 here. Now a1 square plus a2 square plus a3 square plus a0 square plus a here a1 square plus a2 square plus a3 square plus dot 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 up to a6 square plus a7 square is equal to 84 into 7 is equal to 588. And now if a1 is equal to 1, a2 is equal to 2, a3 is equal to 3, a4 is equal to 4, a5 is equal to 5, a6 is equal to 6, and if we put these values, so now in this case 1 square plus 2 square plus 3 square plus 4 square plus 5 square plus 6 square plus a7 square is equal to 588. So here a7 square is equal to 588 minus 91. Here we can see the value of a7 square is equal to 497, and for this the a7 will not the perfect square because 497 is not the perfect square. So we have if a1 is equal to 1, a2 is equal to 2, a3 is equal to 3, a4 is equal to 4, a5 is equal to 5, and a6 is equal to 7, then in this case we have 1 square plus 2 square plus 3 square plus 4 square plus 5 square plus 7 square plus a7 square is equal to 588, and this will imply a7 square is equal to 484, and here a7 is equal to 22, and this will imply n is equal to 22. So we have finally the value of n is 22. In the problem number 26, we have the sum of greatest integral value of x for all real numbers x satisfying the equation 16 plus 15x plus 15x square is equal to the integral value of x to the power 3. So now greatest integer x to the power 3 is equal to 15x square plus 15x plus 16. So now this will be like belongs to x minus 1, and x we are just excluding the value x minus 1 and including the value x. So here this is closed interval, this is open interval, and now this will imply 15x square plus 15x plus 16 belongs to, for this if we are cubic both the sides, then this will be like x minus 1 power 3 and x cube. So this is like x minus 1 whole to the power 3 and x cube. Now x cube is greater than equal to 15x square plus 15x plus 16, and this will imply x to the power 3 minus 15x square minus 15x minus 16 is greater than equal to 0. So this will be like x minus 16 into x square plus x plus 1 is greater than equal to 0, and here x is greater than equal to 16 because this is always positive, because discriminant of this quadratic is negative. So for all real numbers x, this will be positive always, and x minus 16 is greater than equal to 16 here. So now also 15x square plus 15x plus 16 is greater than x cube minus 3x square plus 3x minus 1, and this will imply x cube minus 18x square minus 18x square minus 12x, 15 plus 3 18x square minus 15x minus 3x 12x minus 17 is less than 0. Now let fx is equal to x cube minus 18x square minus 12x minus 17, then f dash x is equal to 3x square minus 36x minus 12. We are using some calculus here, but you must avoid to use calculus, and you can simply find the minimum and maximum value by using the completing square. But here you can see this is 3x square minus 36x minus 12, and here this is basically equal to 3x square minus 12x minus 4, and if we are assuming alpha and beta, and here alpha is less than beta, so the function of alpha will be less than 0. Here we can see the function of alpha will be less than 0. So here fx has only real root f of 18 is equal to minus 233, and f of 19 is equal to 116, and f of alpha is equal to 0, where alpha belongs to 18 and 19 both in open interval. You can see. Now for this equation, when for this equation given when x belongs to 16 and 19, we are including 16 and excluding the value 19. Then in this case we have the greatest integral value of x will be 17, and therefore 15x square, this is for 17 and also for 16. Actually we are taking the value 16, so 16, 17 and 18 are the 3 points. So for the first case, if we are using greatest integral value, which is 16, then this will be like 15x square plus 15x plus 16 is equal to 16 to the power 3, and this is factorizable in terms of x minus 16 into x plus 17 is equal to 0. So here x is equal to 16. This will be satisfied. For the second case, if we are using the value 17, we have used the first value 16, now we are using the value 17. So in this case 15x square plus 15x plus 16 is equal to 16 to the power 3, and this will be like x minus 16 into x plus 17 is equal to 0, and here x equal to 16, and this will satisfy. Now for this is this is for 16 actually. Now for 17, we are just putting the value 15x square plus 15x plus 16, and instead of here we will use 17 to the power 3. So this will be like x equal to minus 15 plus minus a square root of b square, means 15 square minus 4ac, 4 into 16 into 15 by 30, and this will be like greatest integral value of x is equal to 17, and this will satisfy. Now for the third case, if we are using the value 18, now we have the value 18. So in this case x is greater than 19 and x will be less than minus 20. So now we are not receiving any value, any common value, so the sum of we have to mention here, we are not receiving any common value in the interval, so there will be no any value of x from 18. So here total values we have the sum of 16 plus 17, and this is equal to 33. So here total required values are 33. In the problem number 27, we have to draw the diagram as forming a triangle, the obtuse angle triangle ABC, and here P is the point from where the perpendiculars are drawn to AB, BC, CA. This is the point P, this is D, E and F. Also connecting the vertices as F, E and D, and also we are connecting P to B, and we have to mention this angle beta, this angle alpha, this angle beta, this angle 60 minus alpha, and this angle 90 degree minus alpha, and this angle alpha minus 30 degrees. Also we are connecting the angle EAP is 60 degrees minus alpha, and this angle is alpha minus 30 degrees, and also we have to connect this point P to C, and this is 60 degree minus beta, and this is 90 degrees minus alpha. Now this angle is 60 degrees minus beta. So we have now the different points and angles. So here we can observe that EF square is equal to L square into cos square alpha minus 30 degrees plus cos square 60 degrees minus alpha minus 2 root 3 by 2 cos alpha minus 30 degrees into cos alpha minus 60 degrees. Now here we have like L square into root 3 by 2 cos alpha plus 1 by 2 sin alpha whole square plus 1 by 2 cos alpha plus root 3 by 2 sin alpha whole square minus root 3 by 2 cos 2 alpha minus 90 degrees plus root 3 by 2. This is equal to L square into cos square alpha plus sin square alpha plus root 3 by 2 sin alpha into cos alpha minus 3 by 4, and here EF square is equal to L square by 4. The area is equal to root 3 by 4 EF square, and this is equal to root 3 by 4 into 144 by 4 is equal to 9, square root of 3, and the length here we have this L cos alpha minus 30 degrees. So finally we got the value of EF is equal to square root of L by 2, and the area in the form 9 square root of 3. So here we had to find the result, that what is the value of the product Mn. So the value of the product Mn will be 27. Will be the value of the product. In this problem, find the largest positive integer n is less than 30 such that 1 by 2 n to the power 8 plus 3 and 4 minus 4 is not divisible by the square of any prime number. So now in this case we are assuming that let Fn is equal to 1 by 2 into n to the power 8 plus 3 and 4 minus 4, and this is equal to 1 by 2 into n minus 1 into n plus 1 into n square plus 1 into n square plus 1 plus 1 and n square n minus 1 whole square plus 1 for n is equal to 2k plus 1. We have f of 2k plus 1 is equal to half of 2k into 2 into k plus 1, 4k square plus 4k plus 2, and now this is clear that 4 divides f of 2k plus 1 only in the even cases. This is important to mention. Now if we have the only even cases, then n is equal to 28. F of 28 is equal to half of 27 into 29 into 28 square plus 1 into 27 square plus 1 into 29 square plus 1, and clearly for 3 square divides f of 28. So in this case n is equal to 26 and f of 26 is equal to 1 by 2 into 25 into 27 into 25 square plus 1 into 26 square plus 1 into 27 square plus 1, and for the value 5 square divides f of 26 then in this case n is equal to 24, and we have 1 by 2 into 23 into 25 into 24 square plus 1 into 25 square plus 1 into 26 square plus 1, and again we have 5 square divides f of 26, and in this case n equals 22, and f of 22 is equal to 1 by 2 into 21 into 23 into 22 square plus 1 into 21 square plus 1 and 23 square plus 1 we have. Now if we use the case as 5 divides 22 square plus 1 and 5 divides 23 square plus 1, so this will imply 52 divides f of 22, and n equals 20, and f of 20 is equal to 1 by 2 19 into 21 to 20 square plus 1 into 21 square plus 1 into 19 square plus 1, and this is not divisible by any prime square. So here n is equal to 20 is the result we have. So finally we have the number n is equal to 20, which is the largest positive integer, is not divisible by the square of any prime number. Now this is problem number 29. In this problem we have n is equal to 2 to the power 19 into 3 to the power 12, and let m denote the number of positive divisors of n square which are less than n but would not divide n. What is the number found by taking the last 2 digits of m in the same order? So here we have n square is equal to 2 to the power 38 into 3 to the power 24, and now the required number of divisors is equal to 38 plus 1, 24 plus 1 plus 1 by 2 minus 20 into 13. This is 228, and the last 2 digit is 28. So 28 is the required solution. In the problem number 30, let ABC be a right angle triangle. Angle B is equal to 90 degrees. Let the length of altitude BD be equal to 12. What is the minimum possible length of AC given that AC and the perimeter of triangle ABC belongs to integers? Now here AC is equal to 12 times B. So let A plus C is equal to L, where L belongs to integers, and now A square plus C square is equal to L square minus 24B is equal to B square, and for this L square is equal to Lx is equal to 12B, and the two possible values for A and C. Here D is greater than equal to 0, so L square minus 48B is greater than equal to 0, Now b square plus 24l is greater than equal to 0 and b is greater than equal to 24 we have. Now let b is equal to k minus 12. So here k must be greater than equal to 36, and again for l square is equal to k square minus 144, we have simply 144 is equal to k minus l. 144 is equal to k square minus l square. So this is k plus l into k minus l, and here for k is equal to 37, l will be 35. So the minimum value of L we have for k is equal to 37. So here L is equal to 25 is the minimum value. So here we have discussed the past year problems from the Indian Olympiad qualified in mathematics, which is conducted by the Ioqm Center for Science Education with the Tata Institute of Fundamental Research under the aegis of National Board for Higher Mathematics, Department of Atomic Energy, Government of India, and the conducting body is the MTAI, Mathematics Teachers Association of India. And this year in 2025 the exam will be conducted on pan India level on 7th of September, and I hope that you will do better on this examination by reviewing and revising the problems asked in the past years. Thanks.